Hello students, in today's lecture we are going to learn about electric charges and fields, and this is theory part 3. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So, our topic is electric dipole. So, here question arises, what is electric dipole? Electric dipole is a system in which two equal and opposite charges consist. Look at here. In this figure, two equal charges and two equal and opposite charges q and minus q, and they are separated by a small distance 2a. So we known as this is electric dipole. An electric dipole consists of two equal and opposite point charges. So here q and minus q both are equal and opposite, and they are point charges, and they are separated by a small distance 2a. Small distance, the distance between positive charge and negative charge is 2a. And the direction of the dipole, this is the dipole, is defined by the line joining connecting these charges, specifically from minus q to plus q. And the dipole center of the dipole, or we can say midpoint of the dipole, the midpoint is this one. So that is located at the midpoint between two charges. The center located between mid between positions of the charges plus q and minus q. The total charge, the charges q and minus q uh, of an electric dipole is 0, but does not mean its electric field vanishes. And the separation between the charge plus q and minus q prevents their electric fields, comparatively cancelling out when added together. At distance much larger than separation between two charges. Suppose the separation is 2a. If the distance between charge plus q and minus q is much larger as compared to previous one, or we can say r is greater than 2a, in that case the fields of charge plus q and charge minus q nearly cancel out. Consequently, the electric field of dipole decreases more rapidly with distance than the 1 upon r square relationship characteristics of a single charge. It means what? It means we know the electric field, that is denoted by E, is inversely proportional to square of distance, that is E square. So both are inversely proportional. If electric field of a dipole decreases, it means the distance is much much larger, and if the electric field increasing, it means the distance between is small because of their inversely relation. So there is a two charge plus q and minus q. Electric field of a dipole at a point on the axis. So here axis is this one, line joining of the charges. So this shows the axis. Now electric field of a pair of charges, so the pair of charges minus q and plus q, can be determined using Coulomb's law and another principle, that is superposition principle. The results are particularly simple for two cases. First, we determined due to points on dipole axis and points on equatorial plane. So first we consider for points on the axis. So suppose we know the axis representation is this. Look at figure. This is axis representation, and on the axis consider a point. So here point is P. Here we talk about the on the axis. Clear? On the axis. So on the axis point is P. Now we determine the electric field for due to charges on the axis. So consider point P at distance r from the dipole center. Here the dipole center is this one, or we know what is dipole center, the point located between the charges, that is plus q and minus q. So dipole center is this, and the point P, the distance of point P from the dipole center is r. Similarly, we know already the distance between charges is 2a. So r is the distance from the center of the dipole on charge q. The fields due to individual charges are electric field due to charge minus q. This one minus q is equal to minus q divided by 4 pi epsilon naught r plus a whole square p cap. Now here a question. And what is that question? Question is, what is the meaning of r plus a here? Look at here. Here we have to find out the electric field due to charge minus q. And what will be the distance of charge minus q and from minus q to p is r plus a. You know the distance is 2a. So from this from here to here the distance is a, and from here to here distance is a, separated by 2a. It means here we have to find out the electric field due to charge minus q. So the distance from point P of the charge minus q is r. The from point P to center the distance is r, and from center to point charge q is a. So it means r plus a. Or we know the formula of electric field, kq divided by r square. So here r is r plus a whole square. Clear? So electric field due to charge minus q. I hope this is clear. And p cap is the shows the direction. Now electric field due to charge plus q. Plus q. What is the formula? The formula is E plus q. Electric field due to charge plus q is equal to q divided by 4 pi epsilon naught, and the distance from the point P is r minus a. The charge q situated from point P is r minus a. R from point P to charge q is r and minus a. So this distance is a. So r minus a. So it will be r minus a whole square. I hope this is clear. And p cap. So this is the electric field due to charge minus q, and this is the electric field due to charge plus q. Clear? Now what will be the net electric field? So charge, this is a system of dipole, and here we find the a point electric field on a point due to dipole. So the total field becomes E is equal to 1 upon 4 pi epsilon naught 4 AR divided by R square minus A square whole square P cap. This is the total electric field. Now there is some conditions, and what that the condition is, now suppose for R is greater than A, this one, the distance from point P to the center is much greater than A. In that case, what happens? So in that case, the electric field E is equal to 4qa divided by 4 pi epsilon naught R q P cap. Now I repeat it. So suppose R, this R is much greater than A. It means the value of A is negligible. So A will be 0. So substitute the value of A equal to 0. You will be get the electric field, this one. Clear? Let's talk about the direction of the electric field. Firstly, look at here. At point P, due to charge plus Q, the charge is charge is positive, so the electric field towards left, and due to charge minus Q, electric field is in right direction. So this is the net electric field when R is greater than A. So now we will calculate electric field on on a different position. So at a point on the equatorial plane of dipole, we know what is dipole. A system consists of equal and opposite charges plus Q and minus Q. P is the dipole moment, vector of magnitude, this one. So P equal to Q into 2A. So this is the dipole moment, and what is the formula? Charge into the distance between dipole, that is 2A, and directed from minus Q to plus Q. Here a important question, what will be the direction? So it will be minus Q to plus Q. Now we have to find out the electric field on the equatorial plane. So equatorial is, suppose this one, point P situated on a plane. So at point P, we have to find out the electric field due to charge plus Q and due to charge minus Q. So we will calculate step by step. First, we will calculate electric field due to charge plus Q. After that, we will calculate the electric field due to charge minus Q. And then net electric field. So the field's magnitudes are, this is the magnitude of electric field due to charge plus Q. So this is Q divided by 4 pi epsilon naught 1 divided by R square plus A square. This one. Look at here. The distance of charge from point P is what? So this is important. How we can calculate it? So the distance is R square plus A square. Here it means how we can calculate. So it will be the distance from point charge Q to the center is A. Yes or no? And the distance from the center to point P is R. Now we have to calculate this one using the Pythagoras theorem. So what will be this? So this will be under root r square plus a square. Yes or no? So we know the distance of plus charge q from bit to point P is under root r square plus a square. Now substitute in the formula of electric field. The distance square, so the square of distance is what? That is r square plus a square. So this is the magnitude due to positive charge. Similarly, this distance are equal if we talk about the charge minus q. So it will be also under root r square plus a square. Yes or no? So the magnitude of electric field due to charge minus q. Q divided by 4 pi epsilon naught 1 upon distance square, and the distance is r square plus a square. Clear? Now this is the magnitude, and what will be the difference between magnitude of the electric field due to charge plus q and due to charge minus q? There is no difference, because the magnitude term for due to both charges are equal. Clear? Now what will be the net electric magnitude of at point P due to these charges? The directions of electric field due to charge q and electric field due to charge minus q are shown in the figure clearly. So due to charge plus q, direction is always towards in right direction, or we can say away from the charge. Due to nature of the charge is positive. Similarly, due to charge minus q, the electric field away from the charge. So now this is the direction of electric field due to positive charge, and this is the direction due to negative charge. Next question arises, what will be the net electric field at point P? The components of normal to the dipole axis cancel away. The components along the dipole axis add up, and the total electric field is opposite to P cap. We have E is equal to minus electric field due to positive charge plus electric field due to negative charge cos theta P cap. So resolving the component of E and due to charge minus q. So the components normal of the dipole is cancelled out, and the components along the dipole axis is add up. So net electric field at point P is having this direction towards the right of the point P, and this is the term that shows the electric field at point P with direction. So this is very important. Clear? So a point on the equatorial plane of the dipole, P is the dipole moment of the magnitude P is equal to q cross 2a, and directed from minus 2 to plus q. So the field is this one. This is the electric field at point P due to dipole in terms of dipole moment, that is q a multiplied with 2 and divided by 4 pi epsilon naught r square plus a square whole power 3 by 2 with negative sign. Now same, there is a condition, if r, this r is greater than a, in that case what? So in that case the electric field is E is equal to minus q a 2 divided by 4 pi epsilon naught r cube p cap. So this is special case when r is greater than a. So this is the electric field of an electric dipole on the equatorial plane and their special condition. Now, physical significance of dipoles. The dipole moment vector is defined as P is equal to Q cross 2a. Here Q is the charge and 2a is the distance between charges, or we can say distance of the dipole, and P cap is the direction. In terms of P at large distances, on the dipole electric field, on the dipole axis electric field is 2p divided by 4 pi epsilon naught r cube, and on the equatorial plane electric field is minus p divided by 4 pi epsilon naught r cube. The dipole field falls off as 1 upon r cube rather than 1 upon r square. Its magnitude and direction depend on both distance r and angle between position vector r and dipole moment p. So this is the factor on which magnitude of the dipole depends. For a point dipole, 2a is approaches 0. It means what? It means the distance between charges is much small. In that case, q approaches infinity. So p is equal to q into 2a finite. These equations are exact for any r. In most molecules, positive and negative charge centers coincide, resulting in zero dipole moment. And the example of the molecules are carbon dioxide, CH4. Clear? These molecules develop dipole moments only under applied electric fields. However, some molecules have permanent electric dipole moment due to non-coinciding charge centers, making them polar molecules. And the example of the polar molecules are H2O and HCl. Clear? Example: two charges plus minus 10 microcoulomb are placed 5.0 mm apart. Charge is this one. First one is 10 microcoulomb, second one is minus 10 microcoulomb. Suppose we have a Q1 is equal to 10 microcoulomb and Q2 is equal to minus 10 microcoulomb. And both are separated by 0.0 mm apart. Determine the electric field at first is a point P on the axis of the dipole 15 centimeter away from its center O, on the side of positive charge as shown in the figure A. And second is a point Q 15 centimeter away from O on a line passing through O and normal to the axis of the dipole as shown in figure B. So look at here, we have a two figure A and figure B. So we have to find out the correct answer. So using the concept of electric dipole, and here we have to find field. So in first case, a point P, listen carefully, a point P on the axis of dipole. The axis is this one, yes or no? And dipole is consist equal and opposite charges. So minus 10 coulomb and plus 10 microcoulomb, minus 10 microcoulomb and plus 10 microcoulomb. So this satisfy the condition of the dipole. Now we have to find out the field at point P due to charge minus 10 microcoulomb and due to charge plus 10 microcoulomb. Let's see. So Solve this question with me. So electric field at point P due to charge plus 10 microcoulomb. So charge is 10 raised to the power minus 5 coulomb and divided by 4 pi. The value of epsilon naught is 8.854 into 10 raised to the power minus 12 coulomb square per Newton per meter square into 1 upon distance. So distance is 15 minus 0.25 whole square and convert it into meter square. So multiplying with 10 raised to the power minus 4 meter square. So that is given in this question 15 centimeter away from its center. So from center is O, and from the center the distance is 15 centimeter. And from charge from point B to point P, what will be the distance? So distance is 15 minus 15 minus and 0.25, that is 15 minus 0.25. So and taking the square, so the distance is this one. So the overall answer is 4.13 into 10 raised to the power 6 Newton per coulomb, and direction is along BP, B to B, due to charge is positive. Now field at point P due to charge minus 10 microcoulomb. So due to minus 10 microcoulomb, so the again use the formula of electric field on the axial line. So it will be 1 upon 4 pi epsilon naught q divided by distance square. So here q is 10 raised to the power minus 5 coulomb, 4 pi epsilon naught, the value of epsilon naught is this one, into 1 upon distance. So distance from charge minus 10 microcoulomb is 15 plus 2.05 and whole square. Convert it meter square, it will be by multiplying 10 raised to the power minus 4 meter square. Clear? So the net answer is 3.86 into 10 raised to the power 6 Newton per coulomb along PA. Along P to A. In this direction. P to A. Clear? So this is the net electric field when we talk about the electric field on axial line. Now in second case, if we talk about the on equatorial plane, the resultant electric field at point P due to two charges at A and B is 2.7 into 10 raised to the power 5 Newton per coulomb along BP. In this example, the ratio OP divided by OB is quite large, that is 60. Thus, we can expect to get approximately the same result as above by directly using the formula of electric field at a far up away point on the axial axis of the dipole. For a dipole consisting of charge plus minus q and distance is separated by 2a distance apart, the electric field at point R from the center of the axis of the dipole has magnitude, this one, E is equal to 2p divided by 4 pi epsilon naught r cube. R divided by A greater than 1. And where P is equal to 2AQ is magnitude of the dipole. We know the magnitude of the dipole is P is equal to Q into 2A. So this one, this is same. The direction of electric field on the dipole axis is always along the direction of the dipole moment vector. So that is from minus Q to plus Q. Here P is equal to this one, which is equal to 5 into 10 raised to the power minus 8 coulomb meter. Therefore, the value of E is, when we solving, you will be get 2.6 into 10 raised to the power 5 Newton per coulomb. Along the dipole moment direction A to B. which is close to the result obtained earlier. Now, second is field at point Q due to charge plus 10 microcoulomb at point B. Point B is this one. So it will be charge is 10 raised to the power minus 5 coulomb divided by 4 pi epsilon naught values 8.85 into 10 raised to the power minus 12 coulomb square per Newton per meter square into 1 divided by distance is this one 15 square plus 0.25 square into convert it in meter square. So when we solving this, you will be get 3.99 into 10 raised to the power 6 Newton per coulomb along BQ. Along B to Q. This one. Just substitute the all given terms in the formula which we already solved in previous slide. Field at Q at point Q due to charge minus 10 microcoulomb at A. This one. So what will be the field? So it will be charge divided by 4 pi epsilon naught into 1 upon distance. So substitute the value. It will be 10 raised to the power minus 5 coulomb divided by 4 pi 8.854 into 10 raised to the power minus 4 coulomb square per Newton per meter square, and the distance is this one, and convert it in meter square. So when solving this, you will be get 3.99 into 10 raised to the power 6 Newton per coulomb along QA. Along QA. The nature of charge is minus. That's why the direction is away towards the charge. Clear? So clearly, the components of these two forces with equal magnitudes cancel along the direction OQ, but add up along the direction parallel to BA. Therefore, the resultant electric field at point Q due to two charges at A and at B is this one, 2 into 0.25 divided by under root 15 square plus 0.25 whole square and multiply with 3.99 into 10 raised to the power 5 Newton per coulomb along BA. So when we solving this, we will get 1.33 into 10 raised to the power 5 Newton per coulomb along BA. B to A. As in case first, here also we can expect to get approximately the same result by directly using the formula for dipole field at a point on the normal to the axis of the dipole. So the condition is R by A is greater than A. So the formula is P divided by 4 pi epsilon naught R cube. Now this is homework for you. Substitute the value of P and 4 pi epsilon naught R cube. So the value of P is 5 into 10 raised to the power minus 8 coulomb meter, and 4 pi, the value of epsilon naught is this one, and R cube, it means 15 whole cube into 10 raised to the power minus 6 meter cube. So solving this, you will be get 1.33 into 10 raised to the power 5 Newton per coulomb. The direction of electric field in this case is opposite to the direction of dipole moment vector. Again, the result agrees with that obtained before. Thank you for your attention.